Principles of Bioproduct Separation, Module 12, Crystallization, Segment 1, Basic Concept. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. In this module, we will discuss about basic concepts, crystal size distributions, batch crystallization, and recrystallization. At the end of this module, students will be assigned to do several exercises to determine crystal weight and separation factor, determine mass transfer coefficients, determine dominant crystal size and product concentration, determine mass fraction of crystal, determine crystal growth and nucleation rate, and last but not least, determine yield and purity. A crystal is the most highly organized particulate of non-living material that is characterized by an orderly three-dimensional array called the space lattice. The lattice is made up of constituent particles, which can be atoms, ions, or molecules. Crystals exist as polyhedrons having sharp corners and flat sides or faces, and have 7 classes of crystals. For further characteristics of crystals are important and will be discussed in this segment: saturation, purity, nucleation, and single crystal growth. Saturation is the maximum concentration of solute which is thermodynamically stable in solution. Phase equilibria for crystallization result from equal chemical potentials between the solid crystal phase and the surrounding solution called the mother liquor. In many cases, solutions can contain more solute than that present at saturation. Such supersaturated solutions are thermodynamically unstable and can be divided to 3 loosely defined zones as shown in the figure. First, there is a metastable zone, where solute in excess of the equilibrium concentration will deposit on existing crystals, but no new crystal nuclei are formed. Second, there is an intermediate zone where both growth on existing crystals and the formation of new nuclei occur simultaneously. Third, there is a labile zone where nuclei are formed spontaneously from a clear solution. Purity of solute A can be quantified by factor E as shown in equation 1. A similar equation can be written for impurity B as shown in equation 2. Separation factor of the solutes can be calculated using equation 3. If beta is large, the separation can be deemed as effective. Nucleation concerns the genesis of new crystals. Nucleation can result from several mechanisms called homogeneous, heterogeneous, secondary, and attritive. Homogeneous nucleation is the formation of crystals from the liquid phase as a result of supersaturation only. It depends on Brownian motion to generate small clusters of solute molecules in solution. At high supersaturations, the clusters may combine into embryos. The embryos, with a size leading to the formation of macroscopic crystals, are called as nuclei. Heterogeneous nucleation is usually involved in both small and large-scale crystallization. Heterogeneous nucleation results from the presence of insoluble material, which initiates macroscopic crystal growth and consequently avoids the steps of cluster and embryo formation. The solid matter can be dust or small seed crystals. The seeds are usually of the desired product and are especially important as the start of a crystallization. Secondary nucleation is paramount in industrial crystallizers. It is the result of the interaction between existing crystals and of crystal contact within the agitator of the walls of the crystallizer. Alteration is simply the breakup of existing crystals into new particles which grow. Nucleation rate, dN per dt, can be calculated empirically using equation 4. In non-agitated system, growth rate is limited by diffusion and described as diffusion control as shown in equation 5. For agitated systems, agitation increases the relative velocity between the circulating solution and the crystal, and the growth rate often reaches a maximum. Assuming a linear dependence of the reaction rate with supersaturation, the growth rate can be calculated using equation 6. Rate equations like this are difficult to use because the crystal area A varies with the crystal mass m. We cannot connect these quantities if the crystals maintain geometric similarity during growth. That is, if any length remains in a constant ratio with all other lengths. In this case, the arbitrary selection of a single dimension can be used to characterize the size changes. Thus, we define a characteristic crystal length as shown in equation 7 until equation 9. The crystal growth can be calculated using equation 10. For the next segment, we will discuss about crystal size distribution. Until then, I am Yusuf from Institut Teknologi Bandung.